That's not the right screen. There we go. Just gonna wait for people to come, and we'll start. Is that how you guys doing today? Oh, we logged for physics? Yo, what's good, gang? Are we logged for physics? Yes, sir. We gotta get that 5. It's gonna be the easiest 5 of our lives, bro. Trust. Yeah, you talking the lecture channel chat. Mm-hmm. Get people from the physics channel to come. Can you hear me? We can't hear you because this is like a stage channel. But like I can give people the permission to speak, but generally I'm gonna be the one talking. It's gonna be more like a lecture kind of thing. Bum, 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 bum. So how you guys been today? Good. Enjoying the weekend? Why so? Come on. Oh, it's hot where you live. Yeah, 7. Fire. I think people should definitely review Unit 8 more too. Yeah, the exam is kind of stressful. I'm gonna stress about Lang, but you can't really study on Lang. Yeah, like I think fluids though, like they're definitely gonna have a lot of emphasis on it, especially because it's like the first appearance on Physics 1, and there's so many questions they can ask you about it because it was just Physics 2, so they already have so many FRQs and so many multiple choice. So I think we're gonna see a big emphasis on fluids as we progress. I'm gonna wait till like 8:10. Oh, your teacher hasn't gotten through it, yo. That is, yeah. You should start on that, bro. Bernoulli FRQ, bro. Bernoulli FRQ. Honestly, it's not that bad. You just gotta like memorize the. Okay, so what Bernoulli's principle is I'll show you because we're not starting yet, anyways. But Excalibur. All right, so you got like you have pressure, right? Okay, you have pressure. We have kinetic energy per unit volume, and then we have the gravitational potential energy per unit volume. And this is just Bernoulli's equation. It's saying that at any 2 points, this sum is constant. That's basically what it's saying. So it's just the pressure, the pressure, the kinetic energy per unit volume. Because if you think about it, rho is equal to mass over volume, right? It's density. Yeah, it's the pressure at that point. It could be atmospheric. It could be whatever. Then it's just the pressure at that point at the pipe. And so we have basically this is just conservation of energy as it applies to fluids with the addition of this pressure term here. Remember, rho is just mass per unit volume. So this is just regular kinetic energy per volume, and this is just regular gravitational potential per volume. And it's just conserved throughout the entire pipe, the sum. So basically, you can think about it as like mechanical energy is always conserved. which we're going to be going over today in our Unit 3 review here. I have lots of fun questions with LeBron, our glorious king, and yeah. What is pressure? Yeah, I mean, there's not really a good analogy. I guess it would be like quote unquote energy loss to things. So like you know how you have E is equal to E before is equal to E after plus like heat. You could think of it kind of like internal energy or heat that was lost to the system. That's how I think of it. But yeah, kind of like no. You should definitely get on fluids if your teacher hasn't talked about it. It's gonna be on the test a lot, and I already on the practice test. It's like kind of prominent. And yeah, basically you don't have to know for physics one heat, but basically let me just find it. Mechanical energy is not always conserved. Total energy is conserved, right? No matter what the interaction is. But when you have non-conservative forces, which we'll go over today, your mechanical energy might change, and the amount that changes by is lost to as heat or sound because the entire and all energy has to be conserved, and so we call that quantity Q or like internal energy. No, 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 no. Yeah, not chem. We don't got chem up in here, bro. Q equals MCAT. No, 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 no. I guess I think they go into that in physics too, though. Energy lost is heat or heat transfers. Yeah, I haven't taken physics too, but yeah. We gotta get more people. If not, I'll start now. I wanted to get someone. I don't have permissions to ping people. To ping the roll, because we have 30 like 3 interested or press the interested button. If we grab two questions, do it to derive. You can start with the law of gravitation and just get down to there. Where'd you get torque from though? Oh, I see. I see what you got. Yeah. Okay. Yeah. Period. Um, you can. I would just derive it. It's because I don't know if that they're gonna say start with the fundamental physics principle. So like if you go to any deriving question, oh okay, I'm a liar I guess because right here it just says derive it. But generally speaking, they'll say start your response with a fundamental physics principle, and so then you'd start with the law of gravitation, the universal law of gravitation. But yeah, so I would just start with the law. The law is F is equal to negative G m1 m2 over r squared. It's on the reference table, probably. Boom, boom, yeah, right here. Technically, this should be negative because they're saying it's a vector, but whatever. What do you mean by true gravitational force? There's like one actual. I didn't know that was the name, but what we have is gravitational potential energy when you're close to the surface of a planet. So that's like your classic MGH, and then you have the universal law of gravitation, which applies anywhere. What even is G, yo? 6 point. Okay, yeah, there it is. You don't need to know Kepler's law for these tests. This test. Yeah. Like, what? If you look at the course and examiner from Physics One, it's not listed there. Cause I mean, I was looking through this to actually make this, so you don't have to. Where? Kepler's law is not on this sheet, bro. Yeah. All right, so I don't think more people are gonna join, so we're just gonna start. Do 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 do. All right. Wait, I'm actually gonna ping my goat Freddy if you wanna join. Hop on. Hey, what's Kepler's third law again, bro? Kepler's third law. Yeah, this you can derive, yeah. But it's like you got that, man. It's like 3 lines to derive. I can show you guys if you need. Alright, so we're gonna start now. Alright. This is for AB Physics 1. This is a Unit 3 review by me. So, just an overview of the 5 topics we need for Unit 3. The first one is translational kinetic energy. The second one is work. The third one is potential energy. The fourth one is conservation of energy. And then the fifth one is power. Freddie, if you're in, just tell me if you want me to put you as a speaker. But yeah, so on the right hand side, these are all of the equations that you will need to know for the Physics 1 test. Outside of this, there really isn't anything. So we have our classic kinetic energy, our work, our gravitational potential, and then our 2 types of powers here. And we'll go over them in much more detail, as we'll see later on. So first, I think a really big point to touch on is a frame of reference, right? I think classes don't really go enough over this. And so a frame of reference is like a coordinate system that you make to measure the position, velocity, and acceleration of objects. And whenever you draw a free body diagram, whenever you measure a velocity, or literally any quantity for that matter, you're measuring it relative to some frame of reference, right? And there's 2 types of frames of reference. They can either be inertial, which means they're not accelerating, and non-inertial, accelerating or rotating. Generally, an assumption that you can make, as stated on the reference table, is that all systems in Physics 1 are inertial, unless otherwise stated. There are actually some questions that your reference frame is not inertial. For example, the classic, like you're inside of a truck situation, or you're in an elevator that's like accelerating upwards or downwards. And basically what that means is you have to account for an extra force somewhere. But all motion is relative to some chosen frame of reference, right? There's no such thing as an absolute frame of reference. I can't say that something's going 5 meters per second, really. I have to say that something is moving 5 meters per second relative the ground or relative me, because that changes the meaning of that quantity. And as we'll see later on, it changes the values that we actually measure. And yeah, so if you choose a different frame of reference, this will change how certain quantities manifest. And this can be very helpful when you're dealing with the laws that we'll see later in setting our values, choosing a convenient frame of reference so that like many terms cancel out. And yes, this is AB Physics 1, Unit 3. And yeah, make sure you always define a coordinate system when you're given a problem. Define which way is positive, which way is negative. Define your x-axis if you needed, y-axis if needed. Make sure you do all of that so you get a better understanding of where you reside. So what is translational kinetic energy, right? First, what is energy? Energy is the capacity to do work upon a system. And energy is a scalar quantity. So what that means is that energy has no inherent direction. All it's telling you is that I can do this much work in some way, shape, or form. It's not specifying a certain direction, that you can apply this work. Now, you might see energy have a sign, like a positive sign or a negative sign, and those aren't directions of energy per se. It's not encoding like some physical direction in space, but rather it's talking about the actual energy transfer that happens. So if you're talking about the system and you say there's a negative change in energy, that means you lost energy. Or if you're like solving for energy and you got a negative term, that means you lost energy. So that's why sometimes you might see energy have like a negative sign or a positive sign. But energy is a scalar quantity. And yeah, we touched on that. And this is also a very, very important thing to touch on. All energy is relative some frame of reference. No matter what kind of energy it is, the value of it will change depending on what you choose to be your frame of reference. And this is something that we'll see in close detail later on. Translational kinetic energy is the amount of work an object can exert on a system through its motion before coming to rest. And different observers might measure different translational kinetic energies based on their frame of reference. Here is the equation for kinetic energy, 1/2 mv squared, And the units for these are kilograms meters squared per second squared, or joules. That's the common way to do it. And this is also equivalent to Newton meters, kind of, technically, we'll see later. And so, yeah, big takeaways is that different observers measure different translational kinetic energies based on their reference. So, a project check, okay? We got a little diagram here. We got Bob on his bicycle. He's moving 2 meters per second relative to the ground, okay? If the train moves 3 meters per second relative to Bob, and our glorious King LeBron moves 5 meters per second relative to the train, how fast is the goat moving relative to the ground? I'll give you guys like a minute or so to answer that. And once you guys are done, find LeBron's kinetic energy if he weighs 113 kilograms. So I'll give you guys a minute to work on that. Low-key, I gotta pull the answer up because I did and I forgot. Yes, King LeBron is walking 5 meters per second relative to the train. They're all moving the same direction. So just put your answers in chat. Use these 2 bars. I put answer here. When you put your answers in chat, so you don't spoil it for anyone else. And then if you guys are stuck, we'll go over it. Just take a minute. You do the pipes like that to hide your answer. And then when you guys are ready, you can also go on to the kinetic energy question that we have there. So I've seen some people put their they put their answers in chat here, and yes, for number 1, the answer is 10 meters per second. And the way you get that is, so we have Bob moving relative to the ground 2 meters per second, and our train is moving 3 meters per second relative to Bob. So if you assume that Bob was still, then the train would be moving 3 meters per second. But because he's not still relative to the ground, the train is now moving 5 meters per second relative to the ground. And now our glorious king, he's moving 5 meters per second on top of that train. And so how fast is he moving relative to the ground? 5 meters per second plus 5 meters per second is 10 meters per second. And then I think some people put the energies in chat. Yeah, so the answer is 5.7 kilojoules or 5,700 joules, or it's more accurately 5,650 joules. But yeah, you just use the formula that we talked about before. Can I go back? 1/2 mv squared. You plug in the speed here, and then you get your answer. And then those are the answers on the screen there. So next we're gonna go on to 3.2. What is work? Right? So work is the amount of energy that we transfer from a system over a distance through a force. Okay? And a very common thing to understand is that work is energy. Work has the same units. It's just a change in energy. It's the ability to change energy per se. And so consequently work is also a scalar quantity just like energy. And we have our equations for work on the top right here. And what these equations are saying is that work is equal to our force times our displacement, but only in the direction of our displacement. So that's what those 2 bars mean. It means F parallel times our displacement, Or alternatively, you can just write this out explicitly. Our force times the displacement times the cosine of our angle relative displacement. And so another important thing to realize is that only the component of force parallel to displacement contributes to work. If you have a first force perpendicular to the displacement, that force is doing no work because it's not moving relative. It's not moving in the direction of displacement. If you move in the opposite direction of displacement, then you get negative work, and so that's what that sign means there. It's not necessarily talking about our like actual direction in space. It's still a scalar quantity, but relative to that reference, you can be either positive or negative. And so the units of work, yes, it's cosine. And the way to think about why it's cosine versus sine is if it's a really small angle, you want it to be as close as 1 as possible. And because then it's like contributing in that direction. And so cosine of 0 is 1, and so you get the maximum output. But if it's perpendicular, you put in 90 degrees or pi over 2 radians, whatever you want, then you're going to get 0 because it's not at all in the direction there. And so the units of work are Newton times meters or joules. This is a very important distinction. You shouldn't ever write work in Newton meters because when you say Newton meters, you're talking about torque. And they are related concepts, but the difference is when you get to higher levels of math is that you're using a dot product or a cross product. So you're either trying to get something in common or something far away. And so that's where you were confused about the sine or cosine. Because if you're doing torque, where it's the cross product, you'd be using sine instead. But for work, you use cosine because you want it to be in the direction of our displacement there. And so, like we said before, force perpendicular to a body's displacement will do 0 work. And then it's still important to realize though, a force perpendicular to the body can still change the velocity of a body, and we see this in the orbits of planets, right? The actual force is centripetal. It's going towards the center of the orbit. It's acting perpendicular to the planet, but it's still changing the velocity. However, it can't change the kinetic energy, and because it's not changing the kinetic energy, it's doing 0 work. And so you have that kind of scenario there. You can change the kinetic energy while not you can change the velocity while not changing the kinetic energy because it's a scalar quantity. It doesn't depend on the direction. So next slide. We have another progress check based on our applications of work. So a person pushes a box across a rough horizontal floor at a constant speed using a rope angled upwards 30 degrees to the horizontal. The applied force is 100 newtons and the box moves 5 meters. The rope is taut throughout the motion. And so we want to calculate the total work done by the person, by friction, and the net work on the box. And his book mentions, yes, if you're changing when we change the velocity without kinetic energy, we're changing the direction, not the magnitude. Because remember, velocity is a vector quantity, and so changing either its magnitude or direction will cause an acceleration. So that was just some clarification there. And so take some time to crunch the numbers here. And if you have questions, obviously feel free to ask so far. I'll give you guys a minute. Excuse me. Well, you guys ready? Just put the answer in those little pipe bars that I talked about before, the spoiler or run/spoiler, so that you don't spoil the answer for the people. And Charlie, I don't know if you were talking to me, but the test is Thursday, at least for where I am. So yes, I'm taking the test. It's on Thursday. What do you mean by how early should I be? Zapper. Our school instructs us to be 15 minutes before the quoted start date. I would be there like 20 minutes before just to get through all that pre-exam setup and just be comfortable. They can't actually start the test um, until after that time that you're given. All right, so I think I'll let you change your answer, and then I'll reveal the answers. Just something that I've been noticing. Make First of all, make sure to always write your units, and then even when you write your units for energy, make sure you never write it in Newton meters, because when you put it in Newton meters, it gives the implication that it's a torque, and torque is inherently different from energy, and so they will. Well, I don't know if they might be wrong, but it'll be very confusing for the grader. But yeah, the answer was 433 joules for part A, negative 433 joules for part B, and then 0 for part C. So the two things that are important to realize here is that the box is moving at a constant speed, and so the force of it being pulled and the friction force must be equal due to Newton's second law. And so we know that the works that each of the forces do must also be equal and opposite. So because the person did, we just use our work formula from before, the work equals FD cosine theta. You plug in the force, which is 100 newtons. You plug in the theta, which is 30 degrees. And you plug in the displacement, which is 5 meters in this case. And then you should get 433 joules. And because the forces are equal and opposite, the works must also be equal and opposite because they act over the same displacement. And the net work done on the box, you just add all the works together and it's equal to 0. And so, yeah. That was that question. Any questions there? Zappa, what's up, man? So it's the same equation as what do we have? The what's it called? The work done by the person, but the force is now in opposite direction, and so instead of, or the other way you can think about it is that the forces are equal and opposite, and so the works will also be equal and opposite because they're going over the same displacement. And then they have to be equal and opposite because the speed is constant, as I mentioned in the question. It's not 100 newtons in the opposite direction. It's I think 86. It's 100 newtons times cosine 30 degrees. So 87, call it, newtons. But the reason it's equal and opposite is because of the constant speed. You set it equal to, I'll show you. No, the newtons are the same because remember only the x component, or I should say the parallel component of the actual force contributes to the work done. This 100 is the hypotenuse. It's with the y component and the x component. So it's not that the the total like force across the pulling motion is um 100 newtons. It's 100 newtons times cosine 30. So if we go here, we have F net equals F pull. I'm gonna say F net x. F pull plus F friction. So then F pull is equal to negative, alright, this is equal to 0, equals negative F friction. So these are equal and opposite forces. And then you have work is equal to force times displacement times cosine theta. For the person, you have 100 newtons times 5 meters times the cosine of 30 degrees. And this is equal to roughly 430 joules. I think it's 433. And then because these forces for both friction and the pulling are opposite, it's just negative 430 joules for friction. And then the net force, you just add them up. So work friction, I'll just do work F. Work person plus work F is equal to 0. And so if this is 430, and this equals to negative 430. And so that's how you get those answers there. Hopefully that clarified. That sound good? Alright, got you. So, another very important part of the test, the work energy theorem. What is the work energy theorem? The work energy theorem states that the change in an object's translational kinetic energy is equal to the net work done by all of the forces on the object. And we can see the equation there. Delta K is equal to the sum of all the individual works. K means kinetic energy, and that big that big symbol is called sigma, or the summation, right? So we're summing all of the works, and that's equal to our change in kinetic energy. Another important consequence of this theorem, I can prove this theorem for you guys if you want with the calculus, but it's like there's no point. But work is equal to the area under the curve of a graph, contributing force as a function of displacement. So in calculus terms, this is because the integral of force with respect to displacement is the change in energy. And then we have a reworked version of this here. 1/2 m. The change in kinetic energy is equal to 1/2 m v squared minus v naught squared. And we'll do a little question on this right after. And the reason I talked about the calculus is because that's really where the area under the curve thing even comes from, right? Like, if you add up all of the small changes in displacement and multiply them by the small change in force, then you get your total change in kinetic energy. And so, on the progress check here, this question is a little bit more involved than the last two, but it's still doable. So a toy car travels in a straight line on a track at an initial speed of 3 meters per second. Given the motor output of the wheels, find the speed of the toy car. Assume that it's 250 grams, by the way. And then for part 2, you're going to find how long it takes for the toy to come to a stop if the coefficient of static friction between the wheels and the track is 0.6. I'll give you guys some time to answer that. And Charlie, to answer your question for what general topics we need to know. Oh, actually, 1 second. I need to open the door. I'll be right back. Alright, I'm back. So, for Charlie, for what general topics we need to know, so slope of the graphs and the area under the curve. For energy, all you need to know is that the area under the curve for force displacement graph is equal to the change in kinetic energy. And oh, so the question is, how does the graph relate to question one? So using the work energy theorem, find the change in kinetic energy and then get the final speed. But for most things, you need to kind of know, like, okay, if, for example, if you have Hooke's law, right, like F equals negative kx, you need to know that if you graph force against displacement, the slope is the spring constant. Like, you just need to know the formula, and then if you graph one thing against another, what's the slope? That's kind of it. Vuk, I did not get those numbers, unfortunately. And question 2 is asking to find how long it takes for the toy car to come to a stop. So we can go over this question 2, obviously, once everyone submits their answers. So question 1 is asking, you start at this initial speed, right, of 3 meters per second, and then you have a graph of the net force applied by the engine of the car over its displacement, and it's asking, given this graph, find the final speed of the toy car after this takes. So I should have wrote final speed. Yes, final speed. Yeah. And I'll do this question too on the screen. Let's see the answers. It is not, unfortunately. If you guys want me to go over it, then yeah, just tell me. Yeah, I don't know where you got this equation from. I think the value is coincidentally close enough, so I don't think so. And the derived equation is here, I'll show you. It's 1/2 mv squared minus v naught squared. But yeah, like Vuk said, very important thing about this question is that the displacement is given to you in centimeters. I have seen this exact kind of question on the AP where they give you centimeters instead of meters. It's a very, very tricky question that tricks up a lot of people. Make sure you pay attention to the units of the axes when you get them, because it's not always going to be in meters. It's not going to always be your standard units. Sometimes they'll have kilograms and grams, meters and centimeters. Generally, they stay in joules and go to kilojoules. See, yo, now everyone's getting the same answer, so I feel like I had something wrong. But we're gonna go over it, and if we get that answer, then yeah, it would be great. So I'll go over it now. Let me get this here. Oops. Okay, go here. So I should already have this in Excel draw. Yeah. So first you have to get the area of the force displacement graph here. So each of these boxes is 2 units. Let me see what he put. Yes, Kim. Each of these boxes here is 2 units. And so this entire area is 16. This entire area is 12. This is half of 4 because this is 2 boxes. Half of two boxes, that's 2. This is half of 4 boxes, so it's 4. These 2 are 1 box, so it's 1. and this is 2. So if we add this all together, 1 plus 4 plus 4 plus 12 plus 16, that's 37 Newton centimeters. So then you have to convert the Newton centimeters to Newton meters, and then when you convert it to Newton meters, so I'll just do that now actually. Okay, you have 37 Newton centimeters, and then we're gonna go to, this is equal to 1 centimeter, no, 100 centimeters, 1 meter, cancel them out, 0.37 Newton meters. Well, I really just say joules because this is energy. And we're gonna have delta K is equal to our work. So really delta K is equal to K final minus K initial. So that's equal to 1/2 mv squared minus 1/2 mv naught squared. And so this is where that derived equation comes from that I showed before. Okay, we'll just erase this. How do I select over here? And then we just factor the m over 2. And then we equate this to what we had before, 0.37 joules. And then we substitute in our mass also, so 0.37 joules is equal to 250 grams is 0.25 kilograms. I won't even write the conversion out. And then our initial velocity was, I believe, 30 meters per second. Squared, sorry. And then when you solve for v, you will get approximately 3.46 meters per second. That is our final velocity. Does that make sense, everyone? Great. And then the next part was, and yes, you do get decimals in the test. The next part was to find how long it takes for the toy car to come to a stop. And so where is my draw? Here it is. And so basically we just need to go back to our kinematic equations here. We have, it's how long, so we just have the basic definition of velocity. The velocity is equal to the initial velocity plus the acceleration times the change in time. And so we have v, ooh, I should send the link actually, right? There is not yet, I'll send it right now actually. Oopsies. Let me send it right now. Share. And then here. And then also, while you guys are still here, go to that link if you will. Just leave a little bit of a review for me, that'd be great. But yeah, let's go to this question still. So we have v minus v naught over a is equal to our time. And then we have more of this. So our final velocity is going to be 0 here, so we can just get rid of it. It's because we're trying to find out how long it takes for it to stop. So it'll be negative our initial velocity, which is 3.4 meters per second. And now we need to find the acceleration. So the way we find the acceleration is we draw the free body diagram of our little car on the track, right? And the only force that's acting on it is actually friction in the opposite direction, because you have gravity and then the normal force, but they're equal to each other, so they cancel out. So Fx is equal to friction, and then friction is equal to mu times the normal force, which is equal to mu times gravity, because they're equal and opposite here. This is equal to mu 0.25 kilograms. Let me go back here. 0.2 kilograms times 10 newtons per kilogram. Oh, no, you should. You really should. I kind of neglected that here. You should put your velocity vector here. Is equal to 3.46 meters per second. And then you really should also make your coordinate system, which I was stressing before. I was going to hit critical for that. But, well, y is not relevant. So you have like x positive in this direction. And you set like this point equal to 0, what have you. But yeah, could you please tell me? Okay, so right now we're on slide 11, applications of the work energy theorem. And I'm going over question 1 and 2 and how to solve that right now, of course. Yeah. And yeah, so then we have, and do we need to really know no, the physics test does not test for sig figs. They just test reasonable accuracy. Like if you do like 10 decimal places, you're not getting the point. It's like actually there. But if you do 3 decimal places, it's fine. 2 decimal places is fine. I say just have like at maximum 3 decimal places, and then like at minimum 2. And yeah, I'll show how the frame of reference isn't really tied into this. It really ties into more when you have multiple objects. So we'll see that in the later FRQs. And this is equal to our friction here. And if we sum this, you actually had a really nice value. I think it's 1.5 newtons. Also, just so you guys are aware, newtons per kilogram are the same units as meters per second squared, which is actually really helpful for when you're doing your like dimensional analysis or canceling units or whatever. So I like using newtons per kilogram when I'm working with force, because I don't have to worry about the clutter of the other units. But yeah. And so we're going to have this so far. We got 38. That's 4. This is 16. That's 12. That's 2. This is 1. This is 2. Yeah, no, I think I got the right count. Unless I typed it in wrong. 1 plus 4 plus 4 plus 12 plus... No, it's 37. Okay, so... Oh, actually, no, bro's right. They are 1. Because each box is 2, so half of it is 1. So it is 38, you're right. Because each box is 2 units, half the box is 1. Now you're right. And yes, the area under this graph is work, which is also our change in kinetic energy. And yeah, conceptually it doesn't really matter, but it's just semantics. But yeah, so someone asked why it's not negative, and this is exactly why we define our coordinate system here. We're just getting the magnitude of friction for now. And then later when you set up your second law, so you have like F net is equal to, right? You can do negative FF because you know it's in the negative direction. And so that's how you set up the coordinate system. There, and so it is negative. This you're over here just finding the magnitude, and then you assign a direction, which is why I really cannot stress this minus, or putting the the change the axes there. And yes, you do actually do the changing kinetic energy formula inside of equal to there. And no, of course, ask questions. The more questions you ask, the better. I don't know if you can see my screen. Can you see pictures actually? If you can see pictures, I'll just send it here. Charlie, for when you have the FRQs and they ask you to draw the free body diagram, do not put the axis because they're not looking for that. They're only looking for you to identify the forces. Um, However, when you are doing things like in an FRQ, you do want to put like your free body diagram with the axis there, if that makes sense, or like a sketch of the problem. So now we have our net force equal to negative 1/2 newtons here, right? So F net equals ma. And obviously, you can make this a lot more like shorter. I'm just like going through every step so you can see exactly what I'm doing. So ma is equal to negative 1.5 newtons. I want to find the acceleration. I have the force, so I'm just going to divide. A is equal to 0.25 kilograms over negative 1.5 newtons, and this is like either 6, I think it's 6, I don't know, maybe 7. It's 6. And so we have 6 meters per second squared, or negative I should say, because of that sign. Go all the way back to this equation, plug in our negative 6 meters per second squared, and this is equal to our time. And so then these signs cancel, these meters cancel, and so seconds is on top because you do exponent laws, and we're just going to do 3.46 over 6, and that's equal to like 0.58 seconds. And if you get something around here, then you got the right answer, because I used a slightly incorrect area for these calculations. But that is how you do this question. Obviously, you don't have to go so long-winded. You can like honestly put this into like 1 or 2 calculations, but this is all of the work that I just wanted to show you guys, so we got a better understanding of the idea here. Any questions so far? Could you subtract the frictional work by the area under and then do the work there? Okay, so not for this particular question, because if you look at the question, it says it traveled into a rougher part of the track where the friction is this. You cannot find the displacement. If you had a displacement of how, like, if it told you how long, or not how long, but like how far the friction acted upon, then yes, you could find the work done by friction and subtract it from the area, and then get your velocity there. But because this is going until rest, and it doesn't start with friction, you cannot what's it called? You can't just subtract it for this particular problem, but sometimes you can, and yeah. This is stream out. You want me to restream? I'll restream. Is it working for anyone else? Okay, I'm just gonna restream just in case, and then hopefully it works better for some people. So just restreamed. And Zalper asks, if you know the coefficient of static friction, how can you know the kinetic coefficient? And the answer is you cannot know the kinetic coefficient. They're not related in any way. And the only way you can find coefficient of friction is through experimentation. No, because the wheels aren't slipping, it's still in static friction. So if you think about it this way, if we have our diagram here, this really relates to what unit 6's torque. I don't remember. It's probably unit 5. I don't remember. But this really relates more to torque than anything. Change my background color of this. Okay. So if you look at this specific point, right? I'm gonna put the arrow there just to signify. The wheel is only touching the surface at this point. And for the purpose and intent of physics 1, the wheel is not compressing. If you go into physics C, I believe they do some questions on like how the wheel squishes under load and how that affects the friction. But for physics 1, you assume that this is completely rigid, and so this only contacts the ground at one point. At any one time, you're going through like one circumference of the circle as you travel the track, if that makes sense. And so you're never like slipping at all. And because you're not slipping, you're still in static friction. Yeah, well, gears yeah, I mean, they do static friction, I guess. Yeah. Uh, it depends on what you mean by that. Like when gears mesh, right? The teeth do slide past each other, and so that is really kinetic friction. But yeah. If you think of a treadmill, so maybe you think about a pulley. A pulley is slightly different from a gear. So if you have a treadmill, it'd be like going like this. Then yes, this is static friction. If it's wrapped around that pulley and the pulley's rotating, then that is static. Oh, it's not working for you guys now. Yeah. Okay, I'm gonna try again. Hold up. I'll do a low resolution, so maybe that'll like make it more accessible to the bandwidth. 720 at 30. And do this. Okay, does it work now? I use a low resolution, and so like it should use less data. Yeah. Okay, that's great. Great. So as I talked about, this is the wheel. The wheel only contacts the ground at that one point. And for the pulleys, it's contacting it around the entire thing, but it's not slipping at all, and so you're still in static friction. And so that's why you can solve part two. But it's a great question to ask, like whether or not it's in kinetic or static friction. Absolutely. But yeah, we are going to go on to the next question. Charlie asked, when a tire is moving, is it still static friction though because it's gripping the ground? Yes, you're gonna model it as static friction because the wheel isn't slipping. But the second the wheel loses traction, quote unquote, or it skids, then you're in kinetic friction. The second the wheel starts skidding. And so we have systems in place like the ABS in your cars. Basically, what it's doing is it's rapidly braking and unbraking each of your tires to get you back into static friction. Because kinetic friction is generally almost always less than static friction. So when you enter like a skid with your car, right? You're in kinetic friction, and the ABS is trying to rapidly brake and unbrake to get you back into static friction, so you slow down quicker. But that's the analogy for when a tire is moving. I'm sorry, J Video. I sent the slide. I'll send them again, so that you can like follow along. And yeah, if people could like also send screenshots, that'd be pretty helpful too. But yeah, now I'm gonna go on to slide 12 just so people can sync up. Okay, so what is a conservative force? And this is important for our discussions on potential energy. So a conservative force is a force that has the property that when you do work with it, it's path independent. So what that means, it doesn't matter how the sorry, what the displacement path is. All that matters is like where you start and where you end up, and you're gonna get the same amount of work no matter what. And so that's what's meant by a conservative force. And if the work done only relies on the relative positions of the objects, like I said, then the force is conservative. Gravity is a conservative force. The force from a spring is a conservative force. But friction and air resistance aren't conservative forces. And you can think about this for gravity. Think about this intuitively with like, it doesn't matter how the ball, like what kind of path the ball takes after you drop it. All that matters is that it gets from however high you hold it down to the ground. That's what gravitational potential energy is, which we'll see later. Um, and so that's why it is path independent. It doesn't matter what track you take. But friction, the longer your path is, the more friction is going to be done, right? And so it does depend on the path you take in that aspect. And you might have different frictions depending on different paths. And same thing with air resistance, and so those are non-conservative forces. They depend on more than your final initial position. Path dependent doesn't necessarily mean straight line. It's just that it'll change depending on it's dependent on more than your starting and final positions. So it depends on like if you take a curved path, it'll be different than a straight line, if that makes sense. And Theoloff says, so if it's included in the mechanical energy theorem, then it's conservative. Yeah, yes. If your initial state, well, not necessarily equal, but if it's only dependent on the initial state and the final state, then it's conservative. For the purposes of physics 1, all you need to know is that gravity and the spring force are conservative, and everything else is non-conservative. And while you guys go on, I'll just keep going. Okay, so if friction included, then it loses energy, but if gravity is conserved in the sense... that's not necessarily what the what I mean by a conservative force. Actually, okay, I see what you're saying. If mechanical, we're gonna see this in conservation of energy in like 4 slides. But if the mechanical energy is conserved from the force, then it's a conservative force, and we'll touch on that still. We'll touch on that later on. And Zauper asks, so does that mean the total work done by gravity matters from... Zauper, yes, but in terms of like displacement. And Charlie, I'll send you the slides, if that's what you mean. Here are the slides. If you mean where did I get them, I made them. But, yeah. So it depends on like where you start and where you fall. So, and actually, I didn't put this in my slides, but I want to kind of emphasize on this point. And yeah, of course, I want to emphasize this a lot with relation to our frames of reference talk. I'm gonna say this is like, okay, can I draw a straight line? Oh my god, I'm using a mice for all this too, so it's a little harder. Yeah, of course. And this is 10 meters. Okay, I can choose literally any point along this column to be my reference, okay? If I choose this to be my 0 reference, right, this is like 0 meters, then if I held a ball up here, okay, and it dropped, it would have a gravitational potential energy of okay, use equal to mgh. I'm gonna go over this obviously more in depth, but like, let's say this is 1 kilogram because I can't really be bothered. And this would have a gravitational potential of 100 newtons, right? But if I chose to move my 0 down, I now all of a sudden have 150 newtons as my gravitational potential, because it's dependent on where I set the 0. I, as the observer, choose what quote unquote 0 means in the scenario. There's no like physical meaning there, or I shouldn't say there's no physical meaning, but energy is relative to your reference frame. And so when you define your reference frame by setting a 0 somewhere, that's the only that's the only thing energy relies on. So you can have the exact same like physical scenario, But depending on where you measure from, you can have different energies. It just depends on where you set your zero. It's all relative to how far it is from the reference point. So when you have your h, it's really equal to delta y. It's a better way of putting it. But this change in displacement is what matters. And you have the same thing for the kinetic energy too. It's also relative to your reference frame. Because if we go back to the slides before with like LeBron's energy on like relative to the train is gonna change if it was relative to the ground. You know what I mean? Because the velocity is relative to that frame of reference too, and so consequently, so is that the kinetic energy. Is 10 meters considering that you don't take into the account that the height goes negative? If you do this, then well, I was saying the gravitational potential is now like, oh, I see what you're saying. I was thinking up until this point, but if you went all the way down, then it would be negative 5 meters. So you'd have negative 5 times 10, negative 50 Newton, Newton, not newtons, joules. I wrote the wrong units here, chat. It would be negative 50 joules if you went all the way to the bottom, so to speak. Yeah, let's go. But yeah, if you went all the way down, it would be negative 50 joules. Whereas, like, if you set the zero down here, it could be 150 joules. You see how this is the exact same scenario, but just by moving where the zero is from here to like there, you get a completely different answer in terms of like what your gravitational potential is. And I really want to drive this home because this will help you a lot in your problems. And this is actually a question on a lot of multiple choice that I've seen. Not so much FRQs, but in multiple choice, they're going to be asking you relative to something. Yeah, because you get the displacement. So the displacement, okay, if you go from the top to here, it's 15 meters really. And so you could still get 150. But if you consider like just the coordinate, then it'd be 50 there. It depends on how you want to look at it. So if you want to look at it like it goes here and then drops there, relative to zero, it's negative 50 joules. You know what I mean? What do you mean by absolute value of height? Yes, you can have negative energies, as we mentioned before. Energy is a scalar, right? So if you go, okay, where is that? Unit 1, what is frame of reference? Transitional. Energy is a scalar quantity. It doesn't have a direction, but it can have signs, and the sign is dependent on like which way the work is going to go. Oops, that's not it. So you can have a negative GPE, and all that's saying is that like relative to your reference point, right? Because you're at a reference, relative to the reference point, you're going 50 you have 50 joules of energy. Yeah, I got you. So be comfortable with negative energy and be comfortable with negative work. And notice that like, okay, we could define zero here, right, to be in the middle, but that's just not convenient, right? So when we're the observer, we want to make this as convenient as possible. So we'll probably like define it down here, right? And Theolov said, with negative work means it contributes to the motion. No. Positive work means that it's in the same direction as displacement. That's what the sign means for energy. It's against the direction of displacement, not necessarily motion. Actually, I guess it has to be motion also because velocity, but yeah. For like this concept, you're gonna see more in multiple choice. And for the like the also the graph that I had before, this graph, it would be a multiple choice problem. It's not really going to be a short response problem. Like this I've seen on so many multiple choice as I've like been doing practice tests. Power questions are rare. It's towards the end of my thing. I have seen power questions, and it'll be actually exactly the kind of question I have here, which we'll get to. So we're gonna go over that. And yes, power is work over time. More power is the change in energy over time. But yeah, so now that we have that cleared up, if this makes sense, right? We could define all energy is relative to some reference point, and we can choose where the point is. But as the observer, we want to make it really easier for ourselves, so we're just gonna like define it in some convenient like direction, 0. So we don't have to worry about this negative 50 or whatever. We just got the 150 and be nice. So that's like the key takeaway here. Defining things to be convenient for us so that we can get a nice clean answer. And yeah, so I'm gonna go back to the slides if no one else has any questions. You don't have to show your reference point. They're gonna be very good about specifying it. Like if you look at the FRQs, we'll see. They're gonna be talking about the magnitude of the force or talk about relative to the table. So they're gonna kind of give you your reference point. But if you show your reference point and then like translate it over to what they want, then you'll still get the point. So don't worry about that. And generally, people aren't really going to defer from what their reference point is. They might defer in like the direction of what things are. So like here I have this like this is implicitly positive x here, right? Positive x. But you could just as well have this as negative x. You know what I mean? Well, I guess not because 0 is down here. But you could have 0 down here and make this would be negative x, and you get the same number, just a different sign. And so maybe you'll see like a different sign for your answers, but you're kind of gonna get the same point more or less in terms of like actual quantity, like you'll see on the top or on the bottom. But yeah, going back to the slideshow here, and remember guys, we're gonna go over FRQs at the end, so stay tuned for that. I haven't actually done the FRQs, so we're gonna be in it together. But yeah, so we went over this slide. Now, what is potential energy, right? Potential energy is the stored energy within an object due to its position in a system. You need to have at least 2 objects for there to be potential energy, because it needs to be relative to something else, right? And potential energy arises if the objects only interact with conservative forces. So you can have gravitational potential energy because gravity is a conservative force. And the reference point for the 0, like we just talked about this entire time, is decided by the observer for our own convenience. This is a very critical point for physics 1. And here we have the 3 equations that we need to know for gravitational potential. So this is, potential in general. The first one is the spring. So this K is the spring constant, and delta X is the displacement from the equilibrium length, or the equilibrium position of the spring. That's when the net force of the spring is 0. And so it's equal to 1/2 K delta X squared for a spring. And then for gravitational potential, there's 2 forms. The first one is the universal law of gravitation form. We have negative Gm1m2 over r. Very familiar to like the force form that you're familiar with. And then the second one is mg delta y. And this is when you're close to a planet and the acceleration is approximately constant. That's when you'd use this. And you'd use this when you're far away, and then the acceleration is not necessarily constant. Any questions? I believe all of them are in the reference sheet. We can check right now. I have it open. So, okay, maybe I don't have it open. Oh, it's right here. Okay. So, yeah, this is UG here. Yeah, they're all right here actually in order. That's nice. They're over here in the reference sheet. But this is, again, if you're like calculus inclined, you just integrate force with respect to displacement and you can get the energies very trivially. So what that means is like you add a squared or you add an r. You'll see they're very similar to their force variance. So this is like the one for force, it's r squared. But over here it's just r. It's very, very similar. And then also like a derivation for gravitational potential. This is just work if you think about it. The force is mg, gravity, and then the displacement is just delta y. So this really contributes to the fact that like energy, the change in energy is equal to work. And that's that slide. So we'll continue. So what is mechanical energy? Mechanical energy is the sum of systems' kinetic and potential energies. And like I said before, objects only have potential energy if they are in a system with more than one object. And again, this is actually a very important thing to know. There is a very specific multiple choice that I'm thinking of. Maybe you guys know about it. It's like you have two balls. One is in the air, one's close to the ground. It asks you a very tricky question about the relative energies between the balls because they specify the system. And the key takeaway is that if there's only one object, the system can only have kinetic energy. It can't have gravitational potential energy. Because if you want to have gravitational energy, you need like the Earth or something else. So if you only have one object in your system, you won't have any GPE or UG, whatever you have to call it. Next, objects can have potential to do something against nothing. It doesn't make sense, right? The idea of a potential is always relative to something else. If you have potential, it's like you could do something to somewhere, someone. And yeah, so this is the equation for mechanical energy. It's equal to our kinetic energy plus our potential energy. And now we're on this crucial principle, and yes, it's actually that exact question. So it's this question. I think a lot of people got this. I mean, honestly, even I got this wrong when I first did this question. The first two times I did this question, I got this question wrong. Which of the following is correct statement regarding the amount of mechanical energy consisting of only one ball? Right? If it's only the ball, you can't take into account the potential energy. And so you can't use the conservation of energy, which I'm going to talk about right now, to say that they're equal, because they're not, unfortunately. And so this is, again, a tested topic, so make sure you're aware of this. If you only have one object, you cannot use gravity. You can't use gravitational potential. You can only have kinetic energy. And yeah, that's the takeaway for that. So what is the conservation of energy? The principle of the conservation of energy states that the total energy of a system is conserved in all interactions. So no matter what happens, the total energy of a system is conserved. However, the total mechanical energy of the system is only conserved if the interactions occur through conservative forces. So this is an alternative definition of what a conservative force is. What was your question? Oh. Okay, that question. X has more energy than H, or not H, sorry, Y, because X has kinetic energy, but then Y has no kinetic energy. And so X, or whichever one's closest to the ground, has more energy than the one that's above in the ground at rest. Y does have potential, but only if it's in the reference frame of like the Earth ball system. If that makes sense. Because it's just the ball system, you can't have the potential energy. Yeah, exactly. And so you only have the kinetic energies. You have to compare the kinetic energies there. And again, I think this is a really like key topic to understand, because I've seen this on other multiple choice as well. Yeah, X would be more because the gravity would have been work on it, and then it'd have more energy. Like again, they just swapped the reference frame on you. They started with like ball Earth. It doesn't necessarily have to be negative because H is positive here. Like negative, positive, they don't mean anything. It's all relative to whatever you define. Like I can have up be negative or down be positive, or down be negative and up be positive. And this is AP Physics 1, chat. Unit 3, work, energy, and power, and then we'll do some FRQs at the end if you want to stick around. Physics 1. But yeah. So for negative or positive work, again that's relative sum reference, and so you don't really like you can choose whatever direction you want, but they're asking really for the magnitude of it. So yeah. So this is I think someone asked this question earlier, and the total an alternative definition of a conservative force is a force that if you like apply onto a system, the total mechanical energy is still conserved. So if a system like is subjected to gravity, its total mechanical energy will still be the same, and you can see this in the ball question that we have there, right? All of the gravitational potential gets converted to kinetic, assuming like there's no like non-conservative force like friction or air resistance. Um, that all the mechanical energy is conserved there, because gravity is a conservative force and it's the only force acting on the system. So total energy is always conserved in all interactions, but total mechanical energy is only conserved in conservative interactions. And mechanical energy can be lost through heat or sound. So if we had air resistance per se, right, the mechanical energy would not be conserved in that ball dropping scenario because it would be lost to air resistance in the form of heat or sound or what have you. Most likely sound. But yeah, E before equals E after always. And then E mechanical before is equal to E mechanical after plus Q, which is an internal energy. And Charlie, I'm glad it clicked. Now, this is our final topic. What is power? I don't have, well, I have two progress checks after this, but I don't have that many questions. So if you guys want to go over this more, we can. Power is not as tested upon as other topics. But it's still obviously good to know. There's some multiple choice on it. But yeah, power is the rate at which energy changes with respect to time. And average power is the change in energy over the change in time. Work is also a change in energy, and so average power is also equal to the total work done over time. And you can see the equations for that here. So the average power is the change in energy over the change in time, and then that's equal to the work over the change in time. And there is also instantaneous power, which I've honestly never seen this tested before, but someone like asked a question about this, and then also it is in their course exam description, so they have the ability to test you on it. Well, this is instantaneous power, so this is equal to the force times the velocity in that direction, or alternatively force times velocity is times cosine theta. And we can see that here. It's very easy to derive. You have, okay, power. Let me get thicker here. Power is equal to work over time. This is equal to a force times the displacement over time. This is equal to a force times the displacement over time. And that's just velocity. So this is equal to a force times velocity. And so that's equal to power. Specifically instantaneous power. If that makes sense there. Theo left said, I'm sorry if this is quite on topic, but do we need to derive anything in the exam, like period with inertia? Yes, that's actually a very common question. And we will be deriving things when we go over the FRQs here. Like right here, I already derived an expression. And the other one, there's always a derived question for like almost all the FRQs. So be careful about that. I mean, they're pretty easy. You just start with like the principle, and then you go downwards. Also, all the formulas I have are on the reference sheet, so we're chilling. Any questions on this? We have two problems after this. We have one progress check and then one FRQ that I made, and then we're gonna go on to two actual FRQs that we've seen. Alright, so progress check, application of power. Oh, I said the power. But yeah. Two identical cards at the bottom are pulled. Card A reaches in 4 seconds, card B in 8 seconds. Both start and end at rest. Calculate the gravitational potential energy gained by each card. Compare the work done by each motor. Determine and compare the average power output of each motor. And then explain how two motors can do the same amount of work but differ in power. So I'll give you guys like 5 minutes to do this question. Honestly, less. We'll go over in like 3 minutes. Make sure you spoiler your answers. And we'll check it in a bit. See the answers. I don't think you had to memorize Kepler's law. You can derive it easily from the law of gravitation and the period formula. We can go over that too if you guys need. And if you guys have any FRQs you want to do, like, or have questions on, send them right now. Because, after this, when we go over the FRQs, and I don't mind going over any FRQs that you guys want to. I just selected 2 just in case. I'll give you guys like a minute more. You put them in pipes like this, or you can do slash spoiler. I'm gonna go over this question now. So for part A, calculate the gravitational potential energy gained by each cart. So if you recall from the lecture, UG is equal to mg delta y or mgh, whatever you want. So our m's are 3 kilograms, our g's are 10 units per kilogram, and our h is 2 meters. So overall we have 2 times 3 times 10 joules, which is 60 joules. And so they gain 60 joules each. And so the motor has also done 60 joules of work. And the average power output, so for motor A, you have the work done 60 joules. Work is equal to force times displacement, or a change in, it's also equal to the change in energy. We can go over it after if you like. But yeah, so we have our, I'll just pull this up, scattered drop. We have work is equal to the change in energy over time, which is equal to the work over time. So that's equal to, for A, work A, or I say power A, power is equal to 60 joules over 4 seconds. So that's equal to 15 watts. A joule per second is called a watt, just so we're aware. And then for B, it's 60 joules over 8 seconds, which is 7.5 watts. And you guys are probably familiar with watts intuitively, and also maybe even power. So Charlie asked, why do you not factor in cosine theta for work? So if you notice, we don't actually even have the theta, and that's by design. The reason for that is the motor had to do a certain work to drag these carts up. So the amount of energy they gained is the same amount that the motor had to do. J video. Yeah, I'll let you speak if you need. What do you want to speak about? The diagram is like slightly misleading. I just wanted to show the different carts, but well, not different carts, but that A was faster. But it starts at 2 identical carts start at the bottom of a frictionless ramp. So I just wanted, like, the diagram wanted to show that cart A reaches it faster than cart B. You cannot find the offset, no. But the work, you can get the work without the angle or the displacement for like the hypotenuse, because the motor had to do a certain work, and by doing work on the cart gained energy. And what kind of energy to gain? Potential energy. So the amount of work the motor did is the same that the cart gained. All right, great. And so I think we have an FRQ here. You guys want to do this? You guys want to do, this should be M. Or do you guys want to do an actual FRQ? I don't mind either way. This is escape velocity, I think. Yeah, this is escape velocity. Using the physics reference sheet. Yeah, I'm just gonna say FRQ. Or here, actually, this is a reference sheet. Okay, so you guys want to do this one? We can do this one. I'll give you guys like 5 minutes. No, a little bit more. But like to do this FRQ. I hope you have not done this, so I'll do it with you guys after. Alright, I'm gonna start doing this FRQ now. I'm gonna set a picture of it in the chat so you guys can continue to work on it while I do it. Also, it's a good time to fill out this feedback form. But yeah, so we're gonna be doing this FRQ now. Part A. I want a thicker brush. Part A. Write an expression for the total mechanical energy of the probe at the moment of the launch in terms of G, M, and R. So our energy is equal to our kinetic energy plus our potential energy. So this is equal to mv squared, I'll just say this, mv squared over 2 plus, oh I cannot because this is gravitational law. So we'll just do this. mv squared over 2. I'll do minus the gm over r. And so that should do it. Yeah, this is an attractive force and this is a repulsive force. So we're just looking at the signs here. And we need to, it's negative because if you think about this, like the probe, the force is pulling it downwards. So I'll make this negative, and the velocity is going upwards, so that'll be positive. Because if this is my reference frame here, this is this is trying to go downwards, if you know what I mean. But if I'm going upwards, then my velocity is positive. And so the sign of this is just negative because they're in opposite directions. So it's not direct directions, but they go opposite ways, if that makes sense. So if this increases, this will decrease because the radius will increase and this will decrease. And so overall this will stay constant more or less. If that, well, not really, but you know what I mean. So this is in sort of like a balancing act here. If this increases, this will decrease because it'll be farther away from the radius. They don't give us numbers, they only give us the actual letters that we have. So this is the mass of the planet, capital M, and this is the mass of the probe. And this is the radius of the planet. And this is the gravitational constant. So I think that's all there is for A. V is not provided. I mean, I made this question low key. I just kind of glossed over it, but I would also write in terms of V the initial launch speed, because it's not asking for what's it called, the launch velocity yet, or the escape velocity yet. That's part C. But regardless, we'll go on to part B if no one has any questions. Write an expression for the total mechanical energy when it's infinitely far. So when it's infinitely far, basically this R becomes so big that all the potential energy goes bye-bye. And so all you have is kinetic energy. And so you just have, you would set them equal, honestly, if you really wanted to. This velocity isn't well defined, so yeah, I know I'll set them equal. And this will go into part C too. We're just gonna get the escape velocity. So I'll set the kinetic energy equal to my potential energy. And then J video no, because it says kinetic energy. And then it has kinetic energy because what's it called? What we're trying to do is we're trying to get the minimum launch speed required to get it out of the atmosphere. Yeah, and it started from the planet. So like it would have to do work to get out of the planet's gravitational pull, and that work would accelerate it. and give it some velocity. So it has zero potential energy, but it has kinetic energy still. So we set these equals, then we have v squared is equal to 2gm over r. And then v is equal to the square root of 2gm over r. This one I made kind of roughly. I mean, I didn't even do the question, honestly. Which is why, like, for part A, the velocity wasn't even there. Which you kind of have to have. But you just look at the question, look at a general feel for the language. And after this, we're going to be doing actual FRQs. So part D, it says, explain clearly why the escape velocity does not depend on the mass of the probe. The simple answer is that they cancel out. And honestly, that's probably just a valid justification, because both kinetic energy and potential energy are dependent on the mass, and so it's like not a relevant factor, if that makes sense. And so they drop out of the terms. Part E says, suppose the probe is launched at a speed slightly less than escape velocity. Describe qualitatively what happens to the probe motion over time. So it's just going to start entering an orbit probably. Because what's going to happen is if you take this drawing again, so this, it'll be up like here, right? But it'll still be within the region of its pull. So it's not going to have enough to overcome the gravity. And then it'll start falling again. But when it starts falling, the Earth is also, or whatever it is also going to start rotating. And so it'll start going in kind of a planetary orbit here. And it'll orbit around the planet. That's what it will be like qualitatively. Does that make sense to everyone? Now we're going to do actual FRQs. This is 2022 and this is 2024. This one. You ready 2024 in class? If so, just send an FRQ you haven't done before and I'll do it. Preferably with an energy question, but if not, that's fine. Actually, no, let's do an energy question first so we can get used to it. Did you do both of them, 2024 and 2022? Oh, that's tragic. Alright, we're gonna do 2024. We'll do this one. So part A is a block of mass M is released from point A, height 6r above the horizontal. Okay, I'm just gonna copy paste this into my Excel draw. So we're gonna go here, paste it in. Okay. A block of mass M is released from point A, and after it's been released, a block slides on the track. Does not loop clouded with the track, and B and C are at the highest points of the respective loops. All four, so never loop. Okay. Ooh, okay. I did this before too, actually. I didn't realize. So send your answers in chat. Basically, you have to show a diagram of the total energy, both gravitational and kinetic, for when it's located at point B, which is the height 2r over the horizontal, above the horizontal, sorry. Into which part? I'll send this link also. But which part do you want to zoom into here? Yeah. So do part A. I'll do on my screen also. Um, and then you guys can look at it when you are ready. So this first question is fairly simple. So when you guys are ready, just put your graph in chat or like describe what it would look like. What do you mean, Charlie? This one? Well, if you're looking at my screen, this is actually the answer. But you do see this. Yeah. So just describe what you would draw. Or like how many bars on each. You could say like, so we start with 6 bars of potential and 0 bars of kinetic. So then how many bars of potential do we have and how many bars of kinetic do we have? No, that's not correct, Yodia. The part A is worth 2 points. The first point is awarded for showing the conservation event. Hi, Reddy. We're doing FRQs now. If you wanna join in. But the first point is given for applying the conservation of energy, and then the second point is applied for the correct answer. Not just the relative heights. You do have to have the correct answer for this one. So we'll go with the answer now. Because we start with 1, 2, 3, 4, 5, 6 bars of potential energy, and over here we're at a height with 6r. That means that 1r, or I'll do this, 1r, that's too thick, 1r is equal to 1 unit of height. So this is 6 units of height here, right? So 6 units of potential energy. So if we're at point B, the height is 2r, and so we have 2 units of gravitational potential energy, and then 6 minus 2 is equal to 4 units of kinetic energy. So you would get 1 point for having these add up to 6 bars, and then you get another point for having this be 2 units. And in this scenario, the block falls down, yes. The ball does not lose contact with the track at any point. This is a block, and it's not rolling. No, you're good, you're good. So now let's go into part B. Okay. I'll give you guys like a minute to do this one too also. Derive an expression for the speed at block B. This should be relatively straightforward because we just did this graph here. You'll notice in the FRQs, they try to kind of guide you towards the answer. So if you're ever stuck in a later part of a question, just look back at the past part, because chances are that past part is like a quote-unquote stepping stone for solving the next part. They try to kind of structure it that way. So that's a hint for this one too. Just look at the question before that. import this into my little app also. You do have to solve for the velocity, TLF. Or I believe so, right? Yeah, derive an expression for the speed of the block. Yes, good job. Thank you for editing. Good luck, man. Have fun. Of course, bro. If you're asking how do you not misunderstand the question, I would mark up the drawings they give you. So like here, if you look at my screen, I marked up this is 2 units. And I mean, honestly, they tell you it's a block. You can look at it, it's a block. So that one you just gotta read more carefully, I think, and then you'll be fine. But I'll start with this derivation now. So you do need to start with writing a fundamental principle. So people were asking about this before, I think. If you're doing like Kepler's laws or whatever, right, you can't just start with the law. You do have to start with some fundamental principle from the reference book or just in general. So what we're going to do is we're going to start with the conservation of energy. So E before is equal to E after. And then the energy before, all it has is potential energy, right? So we're going to use our graph here. All it has is potential energy. So UG, I'm going to say A for A is equal to UGB plus, we also have kinetic energy in a second diagram, KB. And then we're going to rewrite this further, MGHA is equal to MGHB plus MV squared over 2. Charlie said, could you do all these starting with E naught equals E final, given that energy is not lost? If energy is not lost, then yes, you can. You can actually always do this if it's an energy problem, because this is just saying that energy is conserved. Conservation of energy is always true. Conservation of mechanical energy is not necessarily always true. Like, if it was mechanical energy, then, and some of it was lost, you do have to put like the plus Q. But they're generally not going to ask you about that. But you can always start with this. Okay, so now we're here, and then we're just going to substitute the... first we're going to get rid of all the M's. So this is equal to GHB plus V squared over 2. And next we're going to substitute in the height. So if you go back to the diagram here, we have 6R and then 2R. So I'm going to substitute that in. G 6R is equal to G 2R plus V squared over 2. We're solving for V here. And then I'm just going to rewrite this as v squared over 2 equal to g 6r minus 2r. So v squared is equal to 2g times 4r. V squared is equal to 8gr. V is equal to the square root of 8gr. And this is our final answer here. So Zapper asks, what even is mechanical energy? Mechanical energy, E mech, is just equal to the sum of the kinetic energy and then the potential energy. That's all it is. We'll probably go for another like 30 minutes, maybe less, because we're just going to keep on doing FRQs. Roughly 30 minutes, maybe less. Theolith asks, is mechanical energy kept constant in rockets or explosions? Yes. I believe so. Oh, actually, no. You know why it's not constant? This is also an advanced a problem you'll do in physics C. Mechanical energy isn't conserved because when you have like your rocket, right? When you spit out this gas, you're actually losing mass because you had some like fuel here. You had some fuel here, and so then your mass changes, and because your mass changes, your energy does not change. Or sorry, your energy does change. Sorry, because your mass is changing. So this is when you have to use calculus to figure out your momentum and whatever. Chemical energy is just potential energy. It has the ability to be converted into translational kinetic energy. Yeah. So if you, I don't know if you take AP Chem, but if you do take AP Chem, you know how like whenever you have whenever you have like a PE diagram for like reactions, right? It's for potential energy because it's about potential energy. So chemical energy is potential energy. It's just a smaller scale of potential energy. It's between the actual bonds of the atoms. You don't need to know about the rocket for the test. Like this is a very niche scenario because if an explosion conserves mechanical energy, depends on a lot of factors. But in general, if it's not caused by a non-conservative force, then yes. And for the rocket specifically, this is actually the definition of force for calculus, right? And so this is just momentum over time, changing momentum over time. But this includes the fact that like the mass changes. And so then you have to use calculus now to try to figure this problem out with the rockets because algebra doesn't equip you with the ability to take into account both of these changing at the same time. But yeah. So that is the derivation for part B, I believe. Yes, gravity did work. What is forces versus components? A force is, okay, I'll show you. You can see this easier than component. And Zauber, no, it did not lose energy in total because you're neglecting heat loss and sound loss. It lost mechanical energy because it's at rest now and it's also at zero height. But the heat energy and the sound energy is still there. And that's the bulk of the energy that was from the explosion. So the total energy is always conserved, but the mechanical energy may not always be conserved. Well, the chemical energy inside the explosive, right? That's potential energy. It exploded outwards, right? And so in exploding, some of that chemical energy was converted to heat, and some of it was converted to kinetic energy. Then gravity did work on the kinetic energy to make it go down to zero. And then it lost potential and it lost kinetic. Yes. But that heat, it did lose the heat, but that heat is where most of the energy is. And yeah, Charlie was asking, I think, what is forces versus components? Think about inclined plane problem, right? Um, okay, can I draw? Thank you. So if you just took gravity, right, it would just be this. It would just be well, Fg is equal to mg, right? But if you look at like the components of gravity here, right? This is Fg parallel. Fg parallel is equal to mg sine theta. Given the theta's here, just say that. This mg like parallel, this is a component of the force. This isn't the total force, but it's a part of the gravity force. And if you do write the components, you have to like strike the, or do this little symbol on it to say that you're not double counting the force. Then there's this another one like Fg perpendicular. Well, basically, if you add up all the components, you get the net force. So for this one, it's saying the instant that the block slides through point C. Let me just get this to be red. So there are, oh, that's white. You have red. You have gravity downwards. And then you also have the normal force. Oh my god, alright, whatever then, okay. You can just have two arrows next to each other. So then Fg and Fn. Because the cart is over here, and so it's getting pushed down by the track as well as gravity. And the reason there is normal force is because the block does not lose contact with the track. Yes, F normal N is down. And no, there is no up. First of all, centripetal force is not like a force per se. Centripetal force is the net force of all the forces pointing towards the center. And Fn is, yes, Fn must be greater than Ft. And centripetal also just means center seeking, so it'd actually go down because it's going towards the center. So if you're at the top, you're going to go downwards anyways. But centripetal force is just like net force for the circles. And you know Fn is greater than Fg. This is more related to circular motion. But you know that F net is equal to mv squared over r is equal to, we're going to say Fn plus Fg for this, because they go in the same direction. And then we're going to consider like this portion, right? Fn is equal to mv squared over r minus Fg. But we know that the normal force is non-zero, which means that it has to be greater than gravity. Because alternatively you can write this like Fg is equal to whatever, But this is greater than gravity here. Did I write this wrong? No, that's right. Okay. Why do things topple outward in rotating motion when they go too fast? And the F net, F net is just equal to ma. You just add all the forces. So there's two, you draw your free body diagram. So I drew that here. And then you add the forces. So Fn, I add Fn. Fg, I add Fg. And then Thieleff is saying, why do things topple outward in rotating motion? It's because the velocity is tangential, but the force is perpendicular inwards. So the force goes this way, but the velocity is perpendicular, the tangential velocity, V10. Oh, mv squared over r, this is for circular motion. I don't know if it's on the reference table, we'll find out. It's not on the reference table. Oh no, it is. Here. AC equals v squared over r. So this is centripetal acceleration. No, there are no outward forces. If there was an outward forces, think about it. It wouldn't be a circle if there was an outward force. Well, it wouldn't be a circle if there was a net outside force. Because then it would just fly away. There's nothing to keep in the circle. It needs to be pointed inwards towards the circle. Centripetal force isn't a force. It's like a net force, if that makes sense. Like, it's like saying net force factors in. Net force doesn't factor in. The other forces create net force. So the other forces create centripetal force. Centripetal force is just net force, but for uniform circular motion. So normal and gravity is equal to centripetal. In this case, yes. Because they're both pointing towards the center. If it was outside, okay, if we're gonna go like at the bottom of a point like C, right? Then well, okay, let's do bottom of point B. Then the normal force points upwards, and then gravity points downwards, and so then you have F net. Okay, I can't write there. F net is equal to mv squared over r is equal to Fn minus Fg. This minus sign is very important because this is talking about like Fn is going towards the center, but Fn is going outside the center. So that's what changes if you have the force outside. You just have to draw your free body diagram and then add them to your F9 equation. That's kind of it. So that's all of that. You draw your free body diagram. Okay. So, a student claims that 4r is the minimum height of point A, such that the block can slide through without, where is this? Losing contact with the track after the block is rest. Briefly explain why this claim is incorrect. Oh, this is actually exactly what we just did. Like, literally exactly. But, because basically what it's saying is, I guess you have to look at that. You have to look at the energies, but UG, we'll go back to our energies, here. Basically, it's saying, what if the height was 4r instead of 2r? Hold on, let me find it. No, it's not. It wasn't even 2. Okay, so if you look at C, right, the height is 4r, and so if you started at 4r, if you do the equations again, I'll start from the beginning. We have energy before is equal to energy after, and so we have some gravitational potential at A is equal to the gravitational potential at C plus the kinetic energy at C. So we have mg 4r, because they said assume it's 4r, and then mg also 4r, and then mv squared over 2. If you simplify this, it means that mv squared has to be equal to 0, and so that means that the velocity would have to equal 0, or the mass would have to equal 0. This doesn't make any sense. The mass can't be 0 because it has mass. It said it has mass with mass m. And then the velocity can't be 0 because it said that the block does not lose contact with the track. Charlie, because the question said that what if you started at 4r? So it's saying at point A. It cannot stop at point C because then it's not in uniform circular motion anymore. It just fall. And if it fell, then it would lose contact with the track. Like if it got here and plopped down, it would lose contact with the track for a bit. And it said explicitly that the block does not lose contact with the track. Yeah, C is at the top of the loop. Now you're good. I added 2A to C. Okay, so the reason I added 2A to C is because that's like my reference. Remember how we talking about absolute frame of reference? My reference here is 0 over here. Because this 2R is from the ground 0. So they were saying like from a height 4R. Okay. Well, this C is 2R. Okay, I'm going to get rid of this. It's 2R, but relative to this 0. So we're going to move the 0 down here. And then that's 2r plus r, which is 4r. Won't speed be lost in the loop, so we need to account for that if there is a loss in speed. Speed is not lost because it is frictionless. Yes, all friction forces are negligible. If it's not frictionless, then you had to, then it would start. You would need to have more energy. You couldn't start at 6R. You have to start high, or you'd have to start higher than 4R by a lot to account for the friction. So what you'd have to do, you can't actually do this with you can't do this with algebra. You'd have to do the path integral of this entire path along with friction, and then you'd have to convert that into your height and then start at that height to account for your friction being lost. So you like, but yeah, if there was friction, then you'd have to use calculus to find out what the height is. Anyways, okay, we got this one. Oh, this is question 2. We did that question. Yay, that was a nice question. Free question there. So any questions on the FRQ? We have had a pretty long lecture of like 2 hours and 20 minutes. So if you guys want to call it now, completely fine with that. If you guys want to go over one more FRQ, I can also do that. Forces is weighed the most, I believe. So I'll be unit like 2 probably. I'll check right now. Okay, so forces and translational dynamics, that's 23% of the test. And then right after that is this unit, work, energy, and power. So 23% also. So they're weighted equally for the most. Unit 2 and Unit 3. So this is Unit 3. This is 23% of your test. And fluids should be like a standard of like 15, yeah. Fluids is 15%. And circular motion is a subpoint of dynamics, I believe. So it's 2.9. So it's within that 23%. So it's like, let's call it like, what, 5%, maybe. But it's of the entire test, so it is a lot. You got Calc Gang, I promise you, bro. Alright, one more FRQ. So let's do 20. Oh, you already did 2022, you said. So which FRQ do you guys want to do? Yeah, low-key, I'm pulling a random FIQ from here. The hardest one. Alright, let's do this one, guys. This doesn't look hard, but it's like torque. I haven't prepared for this, so we're just gonna go in it blind. I'm just gonna go through it. So yeah. Draw and label the forces exerted on the beam. Yo, this cannot be right. This is torque, yeah. You guys, if you guys want to do energy FAQ, just send one and I'll do it. Is there energy here? No, there's no energy here, unfortunately. Is energy here? No. There's no more energy on this FAQ. If you want, yeah, sure. Oh, this is actually a good free body diagram to do. I would do it because it's actually kind of tricky. Because this also. I guess you have to do it like this. This is the correct free body diagram for this question. So, I think the trickiest part would be the hinge. Taking into account the hinge here. I don't think people would do that. The gravity is because it acts at the center of the mass. And the tension is easy, you just follow it. But then you also have to take into account the hinge because it's not, you have to cancel out the horizontal component. So like if you have like this kind of invisible component here, you have to cancel it out with that component. And it's because it's pushing against the thing. The free water diagram is what's on my screen. They have to cancel because I believe it says something here. The beam remains horizontal, that's why. So if you didn't have the horizontal components cancel, then the beam would not remain horizontal. Like think about it this way. If you didn't have this force here, that would mean that it would be accelerating to the left also. Like this is clearly not accelerating to the left because it's hitting into the wall. So you need to have something that's stopping it from accelerating to the left. And that's the hinge, which is pushing against it. The tension just follows the string. And then the gravity, it acts on all of these points, but you can it's the same thing if it's uniform density to acting at the center of mass. And then the hinge, again, it's not accelerating to the left. It doesn't make sense for it to. Something should stop it from accelerating to the left, and that's the normal force. Wouldn't the force? The torque would be 0, not the force. The torque. That's because the radius is 0. Because torque is equal to force times radius, right? Because the radius is 0 at the pivot point, the torque is 0. But you can have an infinite force. It doesn't matter. You can have like a 1 1000 Newton force at that point, but you wouldn't have any torque there. Because torque isn't the same thing as force. Well, because like it's obvious that first. Okay, so there's two ways it can. No, you're fine. There's two ways it can fall. It can fall down, or up and down, or it can fall left and right. Right? These are the x-axis and the y-axis. So let's look at just the y-axis. It says it remains horizontal, and then we know it's attached to this hinge. If it remains horizontal and it's attached to the hinge, that means it can't move in the up or down direction, right? And so that means that the gravity here. Wait 1 second. Actually, never mind. The gravity here has to counteract these things pulling it up, right? So because the tension is pulling it up, and then okay, we're gonna talk about why the hinge pulls it up also, but we know that the beam, the tension pulls it up, and then the gravity pulls it down. So why does this now also have to pull up? First, let's consider the left-right motion. Because the beam remains, first of all, it's attached to the hinge, so it can't move. Like, it just cannot move. That doesn't make sense. And it remains horizontal. So the x components have to cancel for all of the forces. So if you have a beam this way, a tension this way, you need to have, at the very least, you need to have a hinge force this way to counteract it. Why is it not horizontal in this case? Because then, okay, so you see how this is kind of made of this force also. This is another component. This is like, call it Fy. Do you agree with that? Well, then this Fy is acting on this hinge at a distance of L, and so that means there'd be a torque. It's not good because that means that it would no longer be horizontal. There'd be an angular acceleration. The gravity here is a force. It's not a torque. No. The entire like hinge is falling, not just one part. G. Ashi. Ashi. The y component of the string equals the hinge force. Yes. Because you have to cancel the torques out. And that's that. This one is just... Okay, so you have F sine theta, remember? This is what we talked about here. So sine of a smaller angle, smaller, yeah, because the y component is less, the actual force must be larger. Because it's still horizontal, it says it remains horizontal. And because the actual force is less, because, yeah, so because the actual force is less, right? It needs to have The actual, sorry, not the force. I need to say the torque or the angle. Sorry, the angle. There we go. Yeah, the tension needs to be more to compensate for the smaller angle because it's still horizontal. So the torque is the same. If the torque is the same and the radius is the same, then the force has to be a lot larger to compensate for the small angle. It was really r sine theta also. And so ft is greater than f1. What do you mean by that? When it's just qualitatively explained, so you can just say like it's small. The angle is smaller, so the force is to be larger. You don't have to use an equation. Oh, actually, if you use an equation, it will actually like you'll lose points because it said beyond referencing equations. So the conceptual thing is like if the torque is the same and the angle is smaller, the force has to be larger to compensate for that. But yeah, okay. So Newton's second law in rotational form. Yay. Okay. Derive the magnitude of the tension in the string expressed in principles. Okay. So we're gonna start with. I'm just gonna write this. Torque net is equal to the moment of inertia times the angular acceleration alpha, and this is equal to our gravity because gravity can't invert torque here, plus the string. Is it plus or minus? It's plus because they're going in the same direction. And then this is equal to 0. And so this is equal to Fg times R. Well, R is L over 2. And then this minus the tension force times this times the angle. That equals 0. And then we have mg L over 2 is equal to ft sine theta L. And this cancels, this cancels. So solve for the magnitude of the tension in the string. Ft is equal to mg 2 sine theta. And that is our answer here. right, Charlie. Yeah, we're gonna end soon, anyways. Thank you for staying through the entire. Oh, before you go. If you haven't already filled out the form, please fill it out. Thank you for staying with us the entire time. Um, I will probably. I don't know. We'll see if I have time. I'll probably host another session. Which unit would you guys want it on? I'm thinking fluids. I'll pull up the units here. I'm thinking fluids. Because it's actually like a hefty chunk, and people don't really know fluids that much. Yeah, it'd be another day. Obviously not now. It'd be. Our test is Thursday, I believe, right? AP schedule 2025. Yeah. Oh wait, no. Oh, it's Friday. Oh. Wait. Oh, we're chilling then. Okay. So we have Monday, Tuesday, Wednesday, Thursday. Wednesday I have Lang. I'm not trying to call Wednesday. But Tuesday, Thursday. I'd actually probably definitely Thursday because prepping for that day. I have it. Yeah, I mean I'm just doing multiple choice really. Lang isn't hard. The S's are easy, but the multiple choice I think is like difficult-ish. You just have to memorize the rubric. That's really it. They expect it to be a draft, so it's like fine. What I think I'll do a review session then, either maybe Wednesday after Lang. I'll see, because I don't want to do it before Lang. So after Lang and then Thursday. Maybe I'll do it Thursday. I'll do fluids Thursday. Alright, guys. Yeah, good luck on calc tomorrow. You have BC or AB? AB, alright, you got this, bro. I believe in you. Oh, wait, yo. There's no point, bro. Like, just do one of them. Alright, bro. Yeah, but if you take BC, you get the AB sub score as well. But yeah, alright, I'll see you later this week. Godspeed, good luck in golf, man. See ya. And I'll head out too. Before everyone goes, please fill out the form. Helps me out a lot. Maybe I'll become a 5-5 member trust. Because right now I'm just a temporary lecturer. So if you fill this out, I get good feedback, I can become an actual member and lecture more, and then yay. So before you guys leave, please. How do I become good enough to teach? Do you like apply? It's the application process is actually really easy, bro. You just like fill out the Google form. I'll send it to you if you want to apply. You just fill out the Google form. I got a response in like less than a day, and then that's it. There wasn't like a screening process, so to speak. 55.org and contribute. Apply to 55. This is the document. You choose whichever role you want. There's 4 sub-teams: survey, FAQ, review section, outreach, website. So if you're like a programming kind of guy, we got the website. Outreach is like, social media. Review section is what I'm trying to do. And you can also be in the materials team. So if you go to 55.org, you see there's a lot of like empty areas for all these courses. So we're trying to get people to fill all this up. But yeah, after exams, of course. But yeah, that's about it. hope you guys enjoyed this session. Try my best. If you guys have any questions, obviously feel free to ask me later on. Just DM me or ping me in the server. Preferably ping me in the server so everyone else can see. So what are my struggles in physics? I gotta practice more, I think. Okay, so I was out. Whenever I'm out for a unit, I get cooked. So I was out for unit 7. And so I'm really rough on unit 7, so I need to review that. But thank you, Charlie. Appreciate it, man. Have a good night, man. Unit 7's oscillations. So that's a simple harmonic motion. The only equations you need to know are like 1/2 ma squared is like the energy. And then it's sine plus phi. This stuff. Yeah, of course, ask away. And then we'll finish up. You cannot find the inertia. Because then I think it would be dependent on the position, the inertia. Actually, no, you can add them all up. Never mind, you can find the inertia. Yes, continue. So, I mean, you know calculus. So what you do is you do a triple integral of like your moment of inertia with respect to x, y, z, and then dx, dy, dz. And that's like I there. A lot of physics is like very intuitive for calculus. I mean, calculus was invented because of physics. You have Newton there. So really, it's like you have like the quantities change. Quantities changing with respect to time is such like a natural thing, right? That you had to kind of develop this concept of derivative for it. I mean, if you look at Newton's laws, he didn't talk about them in terms of forces. He talked about them he didn't talk about them in terms of like MA. He talked about them in dp dt, which is kind of cool. Like he talked about them in terms of like a change in momentum with respect to time, which is what I was talking about before. But like you just look at how things change and how things move. Like if you go back to power, right? Power is like dE dt. To get energy, you can just solve that differential equation, right? Like E is equal to the integral of P with respect to dt. Like you just apply these operations and you get really nice results. So if you add up all of the small powers and with respect to time, you get the change in energy, I should say. It's nice. Yeah. I didn't go over this in the lecture today, but if you like power, like you know how the units are watts, and you know how like things for electricity are also watts. You actually have a very similar equation for power as it relates to electricity. So power is equal to voltage times current. And then voltage is the amount of work per charge, and then current is the amount of charge per time. and then you do chain rule, and you can get also that power is equal to energy over time, just like you started with. And that's why that's where that power comes from in voltage and watts and amps. Okay, center of mass was okay. I don't have it memorized, so I don't know if that's correct. How do you want to apply the calculus for physics? I mean, give me a quantity, right? Like, if there's a delta t, just make it dt. You know what I mean? If there's a delta, you make it a d, and then if there's like, but that's actually is kind of it. And if there's a multiplication, you make it an integral. Well, actually, if there's a sum, you make it an integral. No, when you add things, it becomes an integral. So like kinetic energy is the sum of all the energy. Because that's what an integral is. You're adding up lots of small things. You know how this is the work energy theorem, right? Delta K equals the sums of all the energies, or I should say the work, but it doesn't really matter. Yeah, changing kinetic, this is the work energy theorem. But basically, you just convert the delta to a K. Convert the sum sign to an integral. How you have your energy. Well, that's energy is equal to work, and work is equal to force times displacement. So it's just equal to the integral of force with respect to displacement. And then that's the calculus form, that's it. Because you're adding up the small forces over the small displacements. Like if you have a graph, right? You split it up into really small displacements, and you add those strips up, and that's your change in kinetic energy, because you're just getting the area under the curve there. Oh, because also this is because you know for the energy formulas also, so you know how you have F equals negative kx, right? This is for a spring. If you just integrate this with respect to displacement, like with respect to x, you get the formula for the kinetic energy of a spring. Well, not kinetic energy, but the potential energy of a spring. So this is where these formulas come from, just so you're aware when you integrate. Yeah, I could do that here. I mean, it's actually very simple. Kx dx equals the integral, or k times the integral of x dx. And that's just a standard result. So you have kx squared over 2 plus c. If you integrate force with respect to displacement, you get energy. And that's really important. Well, potential energy of the spring, yeah. And then remember when we had like the gravitational potential also? The universal law? If you, same thing here. Or this one is more general. If you integrate this with respect to the radius, or this r squared, then you also get back the energy formula. Or more or less. That's pretty cool. Yeah. So it's like everywhere. No, I'm a junior right now. Alright, man. Nice talking to you. I'm gonna head out, eat dinner, shower, and then lock in for the rest of this week. We've been on call for 2 hours and 56 minutes. What do you mean by today? No, I'm taking physics right now. I'm taking physics 1 on Friday. Thank you, bro. I would go. No, yeah, no, you're fine. But I would go to all. If you have a teacher, I'd go to AP Classroom and just tell your teacher to release literally every assignment, and do the practice tests, and then do all the FRQs that were released in the last few years, and then you should be set. Do the FRQs that were like released, and then do the multiple choice for the practice test, and then you'll be fine. You're getting a 5. It's really easy to get a 5 in physics 1. Or not really easy, but it's like let's go to Albert, right? It's not. It's actually not that easy. But like, if you get like 25 multiple choice, right? We're gonna bump it up here. This is already a 5, and you got 25 out of 40. You know what I mean? Like, if you get a 70 out of 100, more or less, it's a 5 in physics. Realistically, you're gonna do better on multiple choice, and so you can afford to lose more on the FRQs. I do have a textbook that I use to reference to learn things. Rather, not really prep for the AP. For the AP, I just do AP Classroom because I think it's like the same level probably. But to actually learn it, I use University Physics 18th edition. By yeah, I think that's what it's called. It's yeah, this one by Young and Friedman. I can't give you the PDF, unfortunately. That is illegal, but you can search it up and do what you will. Yep. I got you, bro. Alright. Nice talking to all you. I will be heading out now. Good night, everyone. Of course, bro. I will be hosting another one again probably Thursday. Final review Physics 1 is office hours and probably fluids. So be sure to come for that one. Unfortunately, we didn't get much people this time. I thought we'd get more people. We only got like 10 or so, and then people dwindle off. But hopefully we get a lot more on Thursday. But yeah, I'll see you guys. Good night.